Good morning. This is a numerical from NCRT Exemplar 12.24. Very important numerical to understand the working of a cyclic process and identifying what is happening in each part of the cyclic process. When I say each part of the cyclic process, I mean what is happening during the PV graph or the PV indicator diagram for each component. So for example, this is a completely a cyclic process because it's a closed graph. You can see this is a closed graph, and each of this PV line has a story behind it, and we have to identify that what is the PV graph trying to tell us, and this is the question. Okay, what is happening to the work, what is happening to the energy, what is happening, and since this is a closed graph, this is something very close to a Carnot engine, but this is not a Carnot engine. It looks like one because Carnot engine has two isothermal processes. This has two uh, constant volume processes. If you see, this is a constant volume process and this is a constant isochoric processes, right? Constant volume, and you're given gamma for the gas. We will approach this problem through the lens of concept and reasoning. We will not just blindly do this, okay? So let's read the question first. You are given 1 mole of gas, so N is equal to 1 mole, okay? I hope you know PV is equal to nRT, right? And then what is given to you is that the uh, A to B is a constant volume process noted. B to C, we will apply adiabatic equations. C to D, we will apply again constant volume. And D to A is adiabatic, but you can see it's an adiabatic compression because the motion is leftward. So this is a leftward, right? And then if you talk about other parameters which are given to you, VC is equal to VD is equal to 2VA is equal to 2VB, right? So this is another important information we have which we can use. So data number one, data number two is given to you. A lot of other data are given. Where is the volume constant? We can see from the graph which process is adiabatic. So we are given 1, 2, 3, 4, 5, 6. Six information have been given to us, and a graph is given to us, and we are expected to find multiple parameters of a cycle. So first part is in which part of the cycle heat is supplied to the engine. Now remember, whenever we see these graphs, cyclic processes or PV graph, the first thing that has to strike you is the first law of thermodynamics. First law of thermodynamics, because we're dealing with work done and heat supplied, right? You can see uh, heat supplied, you can see the work done. So all these, what do they indicate? That you have to apply the fundamental, which is this plus the work done, right? First law is the most important law which should strike you to solve these problems. Now let us look at each of the graphs, uh, PV indicator lines, and decide where is the heat is getting supplied. So let's say A to B, right? A to B. If you see A to B, what is happening in A to B? A to B. The A to B, you can see, is a constant volume process. Constant volume process. All right, it's a constant volume process, and you're given, okay, one more important information which you're given is that gamma of the gas is known to you, and the CV, the constant volume specific heat, molar specific heat, which is for 1 mole, is also known to you, and you know what is Cp minus Cv is equal to R, right? So we will use this also if required, right? But basically, we are emphasizing on the first law of thermodynamics. Let's concentrate on the A part of it. I'm just doing A. So A, when I say, what is in which part of the heat? So this is a constant volume process, right? In a constant volume process, the delta V is equal to 0. So the work done is P delta V is equal to P. P is changing, right? So P is changing from here to here. But even if you talk about P not being constant, P is increasing. The net work done is zero because AB has no, remember, AB has no area under it. It's a constant volume process. Delta V is zero. So this has to be zero. No work is being done here, right? In the AB process. Now, if you talk about calculating the change in temperature during A and B, let's do that. P A V A upon T is equal to P B V B upon, okay, T B, right? So the volume is not changing, so these go away. So the pressure, uh, and we also know that the VC is equal to VD, right? So there is no useful information I'm able to extract out of this. So PA multiplied by TB is equal to PB into TA, right? So let's talk about whether we are able to decipher that the, anything is happening here. It's very difficult to identify what's happening in A to B, right? A to B, the volume is constant. Let's talk about B to C. B to C is adiabatic. So heat cannot be supplied to the engine, right? So this is outrightly gone. I'm just leaving it here. I'm just going to B to C. B to C, Q is equal to zero because it's an adiabatic process. Very straightforward, adiabatic process, right? All right. Now let's talk about, we will come and analyze this. Don't worry about it. Let's talk about C to D. Now, C to D is again constant volume process, and we will come and analyze this constant volume process. But the pressure is decreasing here, right? Let's talk about D to A. D to A. It's again adiabatic, so Q is equal to zero. You're not adding any heat or subtracting any heat from the system because it's adiabatic, right? Now our dilemma is, or our confusion is, what's happening in A to B, which is where I started. This is where I started. The second place is, where I started was this, C to D. Even that has to be analyzed very carefully, right? C to D and A to B. If we talk about A to B, which is a constant volume process, I can see that the pressure, I can see that the pressure of B is very high. So let's calculate the TB. Okay, TB is equal to, and I'm using this equation, TB is equal to PB multiplied by TA upon PA. Okay, so I know the pressure at B is very high. You can see the pressure at B is very high. The pressure at PA is low, it's low pressure, and therefore the temperature has gone up, right? Because PB by PA as a ratio, PB by PA as a ratio is greater than 1. So therefore TB by TA is greater than 1 and TB is greater than TA. So the temperature does go up, right? The temperature goes up and the temperature is going up at a constant volume, right? So there is a delta T involved from A to B. So I'm back to this A to B. In A to B, what we have found out is that the temperature increases from TA to TB. It's an increase. This is what we have found out, which means we have a delta T, which is increase in temperature. Increase in temperature, right? So if we were to calculate the change in internal energy, right, of this gas, it will be 1 mole N into constant volume CV into delta T, which is TB minus TA, right? So we know the change in internal energy happens because of change in temperature. And so we know what is the CV TB minus TA. CV is given to be 3 by 2 R. So 3 by 2 R. TB minus TA. This is delta U. Now let's talk about AB in totality. In AB, there is a delta U. So this was A to B. There is no heat added in there is no work done in AB, right? Because it's a constant volume process. In a constant volume process, which is delta V, you cannot have any heat, work done because delta V is zero. So the work done is zero. Let's apply the first law of thermodynamics to AB, okay? So it is equal to Q is equal to delta U plus W. Q is equal to delta U, we have calculated as 3 by 2 R TB minus TA multiply by, sorry, I've already, so N is 1, right, plus 0. So 3 by 2 R TB minus TA is the heat added during the process A to B. I hope this is making sense. We have added heat during the process A to B. The temperature has gone up, the pressure has gone up. Because of that, the temperature has gone up. It and how we have done that? We have applied the straightforward ideal gas equation, right, and found out the final temperature at B, right? Unfortunately, in this numerical, what you find is that the values of, okay, so it is given V2 VA is equal to VA is equal to VB. So we really don't know what is the temperature there at that point of time because the values are not given. So we will have to leave it here because this just question is qualitative in nature. We're not supposed to find how much heat is added. We are supposed to find in which part of the cycle heat is supplied. So we can conclusively say that A to B heat is added. So the part number, first, the answer is A to B heat is added. And how did we do it? We just calculated, qualitatively how the heat got added. Let's talk about the second part. In which part of the heat cycle heat is being given to the surrounding by the engine? All right. Now we've already established that B to C and D to A are adiabatic, so we will eliminate. That leaves us with a choice of C to D, right? In C to D, right? In C to D, if you notice, the pressure has gone down. The pressure goes down. What does it mean? So if I write PC VC upon TC is equal to PD into VD upon TD, right? So this is how it works. I will take you, so we are referring to these 2 points, okay? We are referring to this point and this point. The pressure is going down, volume remains unchanged, right? So C to D is what we are discussing. The pressure goes down, the volume is unchanged. So the temperature at D, the final temperature, is PD into TC upon PC. Now we know PD upon PC. PD, pressure at D upon PC is less than 1. So TD is less than TC, right? So the temperature has dropped, and therefore, if we calculate the change in internal energy, it will be N, which is 1 mole, CV, it's a constant volume process, into delta T. Delta T is negative. So 1 into 3 by 2 R, delta T is a negative quantity. Why is it negative? Because the temperature has dropped. So therefore, delta U will come out to be a negative quantity. What is the work done during C to D? The work done during C to D is 0 because the volume change is 0. The volume from C to D, if you see the figure, the volume from C to D, it's a constant volume process, right? This is a isochoric constant volume process. It says that it's a constant volume process. So let's talk about this. So let's apply law of thermodynamics, first law of thermodynamics. Q is equal to delta U plus W, right? So this is already negative because we have established the delta U will be negative, plus the work done is 0, right? So what you're getting is negative, Q is negative, which means the system, from C to D has rejected the heat. So this is the part of the cycle where this engine, it's not a Carnot engine, it's a hypothetical engine. So Q is lost. Q is lost. from C to D. So we've identified that in which part of the cycle, the heat is being given to the surrounding. So even B to, if we talk about C to D, this is the correct matching, right? Let's talk about what is the total work done by the engine in one cycle. Write your answer in terms of PA, PB, VA. Okay, so we have to find the work done. Now, as already explained to you, we're doing the part 3. We have to find the work done in this cycle, in complete cycle, right? Let's look into the cycle again. If I look into the cycle, there are two parts which I've already identified as constant volume. A to B and C to D are constant volume. No work is done, right? A to B and C to D, work done is 0. Reason is delta V is 0. No change in volume, no change in work. For work to happen, you must have expansion or compression. Let's talk about the other two PV graphs, which are adiabatic in nature. B to C, okay? So let's talk about B to C. This is adiabatic expansion, right? Because the volume is increasing rightwards. Volume is increasing rightwards. Let's talk about another one, right? So let's talk about D to A. D to A, what is happening? D to A is adiabatic compression, right? The volume is decreasing. Volume is decreasing and it is leftward, right? So the volume is going leftward. I'll just show you the figures. The volume is going leftward. You can see the volume is going leftward, right? So we know what is the work done. So the work done where it is the volume is increasing rightward is positive work. Okay, wherever the volume is decreasing leftward, the work done is negative work, right? So B to C is positive work, D to A is negative work. I hope this is making sense. Now we know the processes are adiabatic processes, right? So you must remember, the formula for work done during an adiabatic process. What is the work done during adiabatic process? There is a complete formula for. So what you do, you write the expression for adiabatic process during B to C. We will write that, and then we will write the work done during the adiabatic compression, which is D to A. So the total work done during the cycle A, B, C, D will be actually the sum of work, which is WBC. This is adiabatic expansion plus adiabatic compression. The remaining two, the parts of the PV graph, which are A to B and C to D, contribute nothing. The work done is 0, right? So if you write these two expressions, which are adiabatic expansion, this is adiabatic expansion, I've already mentioned B to C. And if you mention this, you will get the combined work. I will write the expression very shortly, and we will add them and we will get the overall work done during the cyclic process A, B, C, D, right? It's a cyclic process because it's a closed graph. I hope this is making sense. Okay, we will just write it shortly and get the answer in terms of PA, PB, VA. It is just a theoretical exercise and nothing more than. Fourth part is what is the efficiency of this engine, right? So this is a hypothetical engine. Efficiency we know is given by what we want from the engine is the overall work done. So we are calculating this work done A, B, C, D. How much heat did this engine take? Okay, for every part of the energy it took, how much work it did. So this is what you pay for. This is what you know this is your expenditure. Let me put it this way. Q is your expenditure. Where are you doing expenditure? You're doing expenditure in A to B. Remember, you are doing expenditure in A to B because your first law of thermodynamics, yeah, you were gaining, supplying heat from A to B. So A to B was supply of heat. And this supply of heat, some part of it got converted into work done. So you supply something at some cost. So A to B is what you supplied, multiply by 100 gives you the efficiency of the engine. Efficiency of the engine. What I will do now is I will straight away write the expressions for the work done, which is adiabatic process BC and the adiabatic process DA. So I will add the two work dones, both adiabatic in nature. I will divide it with the heat, which is QAB, to find the efficiency. All right. So as promised, I'm writing the expression for work done. So work done during B to C. Okay, B to C. It's an adiabatic process. Just memorize this formula. There is nothing great about it. 1 minus gamma upon P2 V2 minus P1 V1. This is the work done. So if you talk about P2 here, V2 here, it's basically 1 upon 1 minus gamma. And the values are PC, VC minus 1 is P, because you're talking about B to C. So I'm writing work done, which is B to C. PB, VB, right? So let's look into what is known to us, the relationship between VC and VB. So if I go back to the numerical, I know the relationship between VC and PB, right? So I will replace VC with 2 times VB because I want all the answers in this particular A and B. I don't want any answers in C and D. So VC, I can write it as 2VB. So let me just write here as 1 upon 1 minus gamma PC into 2VB minus PB VB. Okay. And so I can take VB outside, VB divided by 1 minus gamma. What is left inside is 2PC minus PB. This is what we are left with. But we do not want the answers in C, right? We don't want any answer in C. So how do we get rid of this? Again, we use thermodynamics, and we know that PV gamma, right, is equal to a constant for a thermodynamics process. So P C VC gamma is equal to PB VB gamma. So PC has to be removed. So PC can be written as PB VB upon VC gamma. I have brought VC gamma on the right hand side, PB, and I am again going to replace VC with 2VB upon gamma. Okay, so this is PB 1 by 2 raised to power gamma. This is called as PC. So we know what is PC now. I'm going to substitute here. So this is 1 upon 1 minus gamma VB, and then I'm going to write PB into 1 by 2 raised to power gamma minus PB. PB. PB is common. So PB VB upon 1 minus gamma. 1 by 2 raised to power gamma minus 1. We want answers in PA, PB, etc. Right? So if you look into the question, it says you want answers only in terms of PA, PB, and VA. You also don't want, it seems they don't want VB. But remember, VB is same as in the question, what is VB? The volume doesn't change. So VA is equal to VB. So I will replace it here as A. So PB multiply by VA divided by 1, because VB is same as VB. It's an remember, A to B is a constant volume process. So VA is equal to VB 1 minus gamma upon half raised to power gamma minus 1. What is the value of gamma given to you? The value of gamma is given in the question, The value is given to be 5 by 3 for the gas, right? So I'll just put the value here. So it is equal to PB multiplied by VA upon 1 minus 5 by 3 is equal to half raised to power 5 by 3 minus 1. Okay, and this is minus 2 by 3, right? And 3 minus 5, so I'll take 3 upwards, minus 3 by 2 PB VA and half raised to power 5 by 3 minus 1. I will take the negative sign inside, 3 by 2 PB into VA 1 minus half raised to 5 by 3. This is your work done during during B to C. And you can see I've got the answer in VA and PB. And you were to express your answer by way of what? You were to express answer in terms of PA, PB. So you have been successful, right? You have been successful. So this is one work you have done, which is the adiabatic expansion. Now let's calculate the work done during the adiabatic compression, the second work done. When you have adiabatic compression, right? And you can see from the discussion so far what is the work we have done in D2A, right? So D2A is the work done, which is equal to W is equal to 1 upon 1 minus gamma is equal to, you know, PdVd minus, it is, if I remember correctly, it is the second work done is from D to A, right? So it will be PD PAVA, right? And 1 upon 1 minus gamma. And we can always write VD. Let's see the relationship between VD and VA, right? So VD is equal to 2 times VA. I will just put it as 2 times VA here. So this is PD multiplies 2 times VA minus PA VA. I can take VA as common, 1 upon 1 minus gamma. VA is common, and 2 times PD minus PA. This is your work done from D to A, which is an adiabatic compression. But we don't want PD, right? The PD is useless for us. So let's use the equations of adiabatic uh, PV process. So P D V D gamma is equal to P A V A gamma. And we don't want this. So P D V D we already know is 2 times VA. 2 VA gamma is equal to P A V A gamma. So P D is equal to P A multiplied by VA gamma upon 2 gamma VA gamma, right? So this goes away. You're left with what? You're left with PA, right? Because VA gamma is getting cancelled on both the sides. You're left with PA upon 2 raised to power gamma. That's your PD. You can always replace PD with this. So this will become VA upon 1 minus gamma and 2 times PA upon 2 raised to power gamma minus P raised to PA, right? So take this also as common and PA as common. So VA PA 1 minus gamma and 2 raised to power 2 by gamma minus 1, right? So this gives you, I can simplify this further, VA PA 1 minus gamma 2 raised to power 1 minus gamma upon 2 minus 1. This is your work done from D to A, which is the adiabatic compression. Adiabatic compression, right? So you have both the works available to you. You have the work done, which is done during the adiabatic expansion, WBC. You also have the work done during the adiabatic compression, which is this, The total work done is the sum of work done during the expansion, adiabatic expansion, and the sum is equal to adiabatic compression. What you need to do now is you just need to add these two works. Okay, you can write this as work done. This is 1, and you can write the value of gamma, by the way, which is 5 by 3 here, or 5 by 3. I will just make it simple. VA PA upon 1 minus 5 by 3 is equal to, I think I don't need to write 2 here anymore because I've taken it in the numerator. So 2 raised to power 1 minus 5 by 3 minus 1 is equal to minus, again the 3 will go up, and what, 2a VA PA 2 raised to power minus 2 by 3 minus 1. You can take the negative sign inside. VA PA 1 minus 2 raised to power minus 2 by 3. So this is your work done from D to A. So let me just add these two work done and try and solve. Okay, so it's 3 by 2 PBVA, right? It's 3 by 2 PBVA into, in the bracket it is 1 minus half raised to power 5 by 3 plus 3 by 2 VA PA, and this is 1 minus 1 upon 2 raised to power 2 by 3. So this is your total work done in this engine, right? This is fairly complicated and a long equation we are getting. We have already calculated what is the heat which has been added to this system. And you can see the heat calculation was done prior to this was this one, right? So we were able to calculate the heat that got added, right? TB minus TA. 3 by 2 R TB minus TA. Right, so 3 by 2 R TB minus TA, right? And what you can do is, if you look into the process of A and B, if you look into A and B were constant volume processes, and I will not, so you can calculate the efficiency is the total work done, which is this complete expression of the work done in the numerator. You can write this in the numerator divided by this, right? So the expression is 3 by 2 PBVA 1 minus 1 by 2 raised to power 5 by 3 plus 3 by 2 VA PA 1 minus 1 by 2 2 raised to power 2 by 3 divided by the efficiency 3 by 2 R TB minus TA. This is the efficiency of this engine. We have just added the adiabatic expansion and adiabatic compression work. Both these together have given the net work. So the resultant work has come by addition of these two quantities. And then we have seen how much heat have we supplied during which process, right? We found the process during which we have added the heat because the internal energy was positive, and we got the answer. So long question in terms of calculation, but otherwise it helps you develop a lot of thinking. What is important is that you should know all the equations for an adiabatic process. A lot of students tend to forget the equations of work done for adiabatic process. They also forget all the equations which link the adiabatic processes, the temperature and pressure, pressure and volume, and pressure and volume and temperature. So memorize all the equations. They'll be very useful in solving these problems. I hope you liked this video. It was a very long one, very exhausting one. And obviously NCERT exemplar has never been easy. But if you see logically, this was not very hard except for the numerical part of it. My channel has 2000 videos in it. Please go through each one of them. Do not miss any of my videos because a lot of explanation has been given, which is not available to you in many classrooms, many websites, and many applications. This is the only channel which is emphasizing on explanation and helping you develop a very strong career base for you. So do subscribe to this channel. You will gain immensely. Thank you very much.